Hello friends, in physics we already studied the 4 chapters and now we start the new chapter and name of chapter is Oscillations. Now from 11th standard or from 6th standard we study the different types of motion. When you see the motion, then some force is necessary to produce or to perform the some motion. There are the different types of motion. First type of motion is a linear motion, oscillatory motion. Second type of motion that we already studied in the first chapter, that is the rotational motion. Then the circular motion, and then now this year we study the oscillatory type of motion. What is the meaning of oscillatory type of motion? When this type of motion is produced, how this motion is produced, and all that part we study in this lecture. Now, there are number of examples of the oscillatory type of motion. Now, the first example, the best example is the needle of the sewing machine. When you paddle the sewing machine, then the needle performs up and down motion continuously. The motion it will be looks like this: down, up. In this way, it performs the up and down motion. That is the needle of sewing machine. Another type of motion is the motion of the swing. Okay, swing is tight, and when you apply the force to the swing, then it performs to and fro motion about the same path. Okay, then motion of a swing, motion of the needle of the sewing machine, then the motion of the cradle. These are the different examples of the oscillatory type of motion. Oscillatory type of motion means the motion of the body which most probably it will be either to and fro or it is up and down. Okay, either it is up and down or to and fro, then that motion is called as the oscillatory type of motion. There are number of examples of the oscillatory type of motion. This oscillatory type of motion is again of two types. One is linear type of motion and angular type of motion. First of all, see, this motion is either to and fro or up and down. Up and down means it is a up and down, and to and fro in this way. It is a to and fro about the same path, about the same trajectory, or about the it traces the same path. That type of motion is the oscillatory type of motion, or its movement is same during its motion. Then that motion is called as the oscillatory type of motion. To perform this any one movement, to perform any one oscillation, means suppose this is the sewing machine. This is the swing is tied here, and this is its main position. Now this swing moves forward, okay, again it moves backward, again it moves forward, and comes to its initial position. Okay, in this, suppose this is my one swing and the swing is tied here. Okay, it performs up and down motion. This is its initial position. It moves forward, it moves backward, and again comes to its initial position. Then we say that it completes its one oscillation. Okay, when it's complete one oscillation, some time is required to complete the oscillation. Whatever is the time required to complete the oscillation, that time is called as the period, or the another name is periodic time. Very simple. The time taken by body to complete to and fro motion or up and down motion about the same movement, about the same path, then that time is called as a period or the periodic motion. if it takes same time, okay, if it takes same time for each movement, for each motion, for each oscillation, then we say that the motion is periodic motion. Don't confuse here, okay? Periodic motion is totally different and oscillatory motion is totally different. Oscillatory motion is only oscillatory motion is meaning is very simple. If the motion of a body is to and fro or up and down about the same path, then it is oscillatory motion. Periodic motion means the motion of a body to complete one oscillation of a body, it requires same time for each movement. Then the motion is called as the periodic motion. Okay, if it requires same time, for example, motion of earth around the sun, that motion is a revolutionary motion. It requires 365 days to complete one revolution around the sun. For every revolution, it requires 365 days, 365 days. So that motion is called as the periodic motion because then the period is same. Motion of earth itself, okay, that is it requires a time period of 24 hours. It is the same everywhere, so that motion is a periodic motion. And oscillatory motion means needle of sailing machine. It is not same, its period is not same for every time. Swing, for each to and fro motion, swing does not take the same time. Okay, first it take very less time, but as it performs motion without any external force, it requires more time because some energy loses at that time. Its period is not the same, its time period is not the same. Therefore, oscillatory motion is not, every oscillatory motion is not a periodic motion. Remember that. Every oscillatory motion is not a periodic motion. But every periodic motion is a oscillatory motion. This is the most important and confusing statement. Every oscillatory motion is not a periodic motion because for every oscillation time period is not the same. Okay, so every oscillatory motion is not a periodic motion, but every periodic motion is a oscillatory motion. Okay, write down this statement. Every oscillatory motion is not a periodic motion, but every periodic motion is a oscillatory motion. Now in this chapter we study the simple harmonic motion. What is the simple harmonic motion? If the body performs to and fro motion, up and down motion, and it traces the same path, it follows the same movement again and again, means it repeats again and again, then that motion is called as the harmonic motion. And this is the simple harmonic motion. What is the simple harmonic motion? When we study the simple harmonic motion, in short, we say it's a SHM. Most probably, oscillation, this chapter is also called as a simple SHM. Okay. Now, SHM, there are the two types of SHM. One is the linear SHM and second one is the angular SHM. Now, what is the difference between, what is the meaning of linear SHM and the angular SHM? Meaning is very simple. If the body performing simple harmonic motion, what is the meaning of simple harmonic motion? Simple harmonic motion means body performing oscillatory motion and its time period is the same. Then that motion is a harmonic motion. And if it follows the same path, it follows the linear path, then means it completes or it travels along a straight line path. Either it is a to and fro or up and down, then the motion is called as the linear simple harmonic motion. And if the body performing simple harmonic motion and it traces arc or circular path, then the motion is called as the angular motion. Means in linear motion we measure linear displacement, linear velocity, linear acceleration, and the required term is the force. And in angular SHM we measure angular displacement, angular velocity, angular acceleration, and the required quantity is the torque, tau. Okay, this is a basic or simple difference between the linear SHM and the angular SHM. Now we see the differential equation of the linear simple harmonic motion. How you produce the differential equation of the linear simple harmonic motion? Before that, before writing the linear differential equation of linear simple harmonic motion, just we see the simple three cases. Okay, now this is my result support. Okay, one string is there, and do the string and fix one block whose mass is small m, and this is my string. Okay, now this is a relaxed position of the string. Means there is no any external force on the string, and one more force is 0. Means here what? Capital F is my external force. Okay, that force is a 0. If the capital F is 0, means external force is 0. Obviously, the displacement, which will be symbolically expressed by x, okay, that is also 0. Now, when I apply force on this block towards the right, okay, I am applying the force on this block towards the right, towards this right. This is my external force with my hands. Then this spring, not a string, S-P-R-I-N-G, this spring is stretched. And this will be the new position of the spring. Okay, this is the initial position of the spring, and this will be the new position of the spring. At that time, the displacement of the spring is x, and this displacement is a positive or negative? Yes, let's see, it's a positive. Okay, here the force is applied, external force is applied. In which direction? Towards right side. Okay, when force is applied, then the displacement is positive. But what is the natural tendency of the spring? What is the natural tendency of the spring? Natural tendency of the spring is always maintain its initial position, natural position. This is the after a stretching. Without stretching, the spring it will be in the relaxed position. It will be in the relaxed. It will be in a stationary position. So the some force is inside the spring. That force is called as the restoring force, and this restoring force tends to spring towards the disc, okay, towards the rigid support. So at that time, this equation becomes F equals to minus of kx. Now question arises, so what is the k? Okay, whatever be the external force, that much amount of displacement. Okay, that much amount of displacement. If I increase the external force, displacement is also increases. Okay, is it clear for everyone? As I increase the external force, displacement is goes on increasing. Okay. So as the external force increases, displacement increases, but the spring again comes to its initial position. So the internal restoring force is also at displacement towards the right, and that internal restoring force works towards the left, means both are opposite to each other and both are proportional. To remove that proportionality sign, we add a one constant. Okay, and that internal restoring force bring that block towards left, and the block is moving towards right because of what? Because of external force. So my equation becomes F equals to minus of Kx. And what is that K? Just I am writing one more symbol, that K is my force constant. Okay. Now, when I remove the external force which is applied towards this right side, okay, external force is applied towards right side. Now I am removing that force. Then what happens? Then that spring is compressed. That spring is compressed. Now, when the spring is compressed, at that time, comparing to the displacement, its displacement is negative because the displacement is towards this left. Spring is compressed. Okay. Now, what is the natural tendency of the spring? To maintain the relaxed position. Means the spring push this block towards the right side. Okay. So restoring force and displacement are again opposite. Add one spring constant and we are getting an equation F equals to minus of Kx. Means during the relaxed position, no external force, no internal restoring force, and no displacement. When stretching the spring, displacement is positive in the direction of external force, opposite to direction of restoring force. So F equals to minus of Kx. This small f is a restoring force. During compressed position, displacement is negative towards left. External force, no. Restoring force towards right. Displacement towards left. So both are opposite to each other. But remember, force is a vector, displacement is a vector. So I am writing this F equals to, we are getting this equation F equals to minus of Kx. If someone wants, then draw one short diagram so we get easily understand. Okay. Now see the part. Same part, but now we are interested in the mathematical part. In this simple harmonic motion, we are getting one equation F, that is the restoring force, equals to what? Minus of H. So I am writing here internal restoring force is given by F equals to minus of H. But as per Newton's second law, it is a motion. As per Newton's second law, F equals to mass into acceleration. So we are equating these two. Mass into acceleration equals to minus of kx. So mass as is. Okay. What is the acceleration? Acceleration is a very simple thing. Acceleration means what? Rate of change of velocity per unit time. So I am writing here, instead of acceleration, dv by dt equals to minus of kx. Acceleration means rate of change of velocity per unit time. So m into dv by dt equals to minus of kx. d by dt as it is. But what is this velocity? Because here the term is displacement. What is the velocity? Again, velocity is nothing but rate of change of displacement per unit time. So it becomes a dx by dt equals to minus of kx. So we are writing here m d by dt of dx by dt. Just instead of that, we have to write down d2x by dt square equals to minus of this x. Make a term on one side, m into d2x by dt square plus kx equals to 0 divided by m on both the sides. So we are getting, after dividing the m, so here m get cancelled, plus k by m into x equals to 0. But what is that k by m? That we have to find out. What is the k by m that we have to find out? But that k by m is nothing but my omega square. How you write down that omega square that we have to see, and what is the new form of that differential equation? K by m equals to omega square. So my equation becomes d2x by dt square plus omega square is equals to 0. This is my differential equation. This is one more form of differential equation. Okay, these are the differential equations of linear simple harmonic motion. But before studying that differential equation, just we come to this part. M by m into a equals to minus of kx. It gives a one definition of acceleration. Okay, m into a equals to minus of a into x. But what is this m? M means my force. Okay, so F equals to minus of a into x. This part is clear. Let k is my spring constant. So can I write F is directly proportional to minus of x? If I concentrate on this term, it will be very clear. If magnitude of force is directly proportional to magnitude of displacement, and their directions means what? Direction of force and direction of displacement, and their directions are exactly opposite to each other. Just see once again. Magnitude of force and displacement are directly proportional to each other and their directions are opposite to each other, then such a motion is called as the linear simple harmonic motion. Through this mathematical part, we can easily understand the definition of the simple harmonic motion, or this is simply the condition for the simple harmonic motion. That is, magnitude of force and displacement are directly proportional. Magnitude of force and magnitude of displacement are directly proportional to each other and their directions are opposite to each other. Then such a type of motion is called as the linear simple harmonic motion. Means what is the condition of linear SHM? Then it will be very simple, sir. F is directly proportional to minus x. This is a simple condition of SHM. Or some students write in this way: force is given by mass into acceleration equals to minus of kx. So acceleration equals to minus k by m into x. Again, k is a force constant, m that is the mass of block, which is also constant. Means again, this all the term is constant, or simply gravity. Acceleration is directly proportional to minus x. From this we again conclude that magnitude of acceleration and magnitude of displacement both are directly proportional to each other and their directions are opposite to each other. That type of motion is called as the linear simple harmonic motion. Means we are getting the two sets. One is F is proportional to minus x and A is proportional to minus x. These are the two sets of the simple harmonic motion. Okay, is it clear for everyone? Yes. Okay, now we see the next one, which is a very easy and that part is very easy and it is very simple. Now we are studying the differential equation of linear simple harmonic motion. But what is the value of, what is the equation, what is the formula, value of acceleration, velocity and displacement for a linear simple harmonic motion, that we have to see one by one. Okay. So the first thing that we study, the acceleration of a particle performing SSM. So I am writing only the acceleration, and then using the symbol AC instead of only A, because in this chapter A means my amplitude. Okay, so we don't confuse this. Acceleration. The differential equation of linear SSM is it will be very simple. Just we study that d2x by dt square plus omega square is equals to 0. What is this d2x by dt square? d2x by dt square is nothing but, can I write that d2x by dt square in this way? That is a d by dt of dx by dt. What is this dx by dt? This dx by dt is nothing but, that is my velocity. What is this dv by dt? dv by dt means my acceleration. So now it will be very simple. d2x by dt square means my acceleration. Acceleration means double derivative of displacement with respect to time. Acceleration means single derivative of velocity with respect to time. Okay, in terms of differentiation we can also this acceleration. Okay, so d2x by dt square plus omega square is equals to 0, and this d2x by dt square is nothing but my acceleration. So I am writing here the d2x by dt square equals to minus omega square into x, or simply the acceleration of a particle performing SHM is given by formula minus of omega square into x. This is the most important formula of this chapter. That is, acceleration of a particle is given by omega square minus of omega square x. But in numericals, most of numericals, the question is like this: calculate the acceleration of the particle, and in that question the examiner asks only the magnitude, not the direction. Here the direction is clear that negative indicates what? Acceleration and displacement both are oppositely directed. Their directions are opposite to each other. Just they ask only the magnitude. So we can easily write. In some numericals we require omega square means k by m. Okay, and from that they ask what is the k, what is the m. That k is my spring constant, m is the mass of that block or mass of the object which performs the motion in this. Now the second part of this expression, that is the velocity of a particle performing SSM. That is the velocity, symbolically it will be v. Now we have to find out the velocity of a particle performing SHM. Now we are getting acceleration is given by minus omega square x, and this acceleration, just like writing here, acceleration is nothing but dv by dt equals to minus of omega square into x. Just add, multiply and divide by dx. Okay. So my equation becomes CL dv by dt into dx by dt dx equals to minus of omega square x. Don't cancel this part. Okay. So dv by dx by dx into dx by dt equals to omega square x. what is this dx by dt? That is a change in displacement per unit time, or single derivative of displacement with respect to time, means my velocity. So instead of dx by dt, I am writing velocity into dv by dx equals to minus of omega square x. This dx goes to this side, so my term becomes v into dv equals to minus omega square x into dx. Now this is a term dv, this term is a dx. Now in this here we are getting a differentiation. To remove that differentiation we require the integration. Okay, so integrate this equation. So after integrating, or on integrating, integration of v dv equals to integration of minus omega square x into dx. The term which are constant, that are out of integration, here v is not a constant, but omega square is a constant, because omega square equals to k by m. K is my spring constant and m is my mass of the block. So I am writing same term here, v into dv equals to minus omega square x into dx. Again we require the simple general formula for the integration. What is the integration of x raised to n? Just I am writing here this side, integration of x raised to n dx equals to x raised to n plus 1 divided by n plus 1. I am using this formula here. Okay, so integration of v is a v square by 2, okay, equals to minus of omega square, integration of that is a x square by 2 plus c. What is the c? C is my constant of integration. So I am getting the equation v square by 2 equals to omega minus omega square x square by 2 plus c. Don't cancel this 2, because the denominator of c is not present, means its value is a 1, not a 2. So don't cancel this. Now we have to find out the value of that c first. Okay, to find out the value of c, let's consider one condition. To find out the value of c, just consider the one condition. Okay, to find c, if I want to find out the value of c, means which term becomes a 0, that we have to see. Okay, to find out the value of c, which term becomes a 0. Now it will be very clear, this term becomes a 0. V square by 2 becomes a 0, means velocity becomes a 0. And when velocity becomes a 0, it will be very simple to find c. Consider extreme condition. What is the extreme condition? Okay, just take one example of the cricket pitch. This is my cricket ground. This is a pitch, and the batsman is present. Bowler throws a ball. This is exactly the mean position. This is the extreme position. These are extreme position, because ball moves this side, or ball moves maximum up to the backs. When bowler throws a ball towards the batsman, then batsman strike to the ball. When the speed of ball is maximum, at the mean position or at the extreme position, when the batsman strikes the ball, the speed of ball is maximum at the mean position. Okay, and as the ball moves forward, the speed of ball goes on decreasing. खूप हळू मारला असेल तर पॉसिबल नाही आहे की बॉल बाउंड्री लाईनला पोहोचेल पण असं. ओके, सो स्पीड ऑफ द बॉल गोज ऑन डिक्रीजिंग 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 and finally it reaches to the boundary line or the extreme condition. Means at the extreme condition, velocity of the ball is 0 and at that time the displacement is a maximum, and that maximum displacement is called as the amplitude. Here we are getting the new word amplitude. Maximum displacement is called as the amplitude. So I am writing to find the C, value of C, consider the extreme condition, and the extreme condition velocity is 0 and displacement is amplitude. Just I am writing here A stands for amplitude, and meaning of amplitude is what? Maximum displacement from mean position is the amplitude. So my term becomes 0 equals to minus of omega square s square by 2 c, or c equals to omega square s square by 2. Just like this is my first equation, this is the second equation. Substitute value of c in a first. Value of c in the first, so it becomes v square by 2 equals to minus of omega square x square upon 2 plus omega square a square upon 2. Now see the remaining part. It is very easy, not difficult. Okay, so it becomes a v square. There is a 2 is a common denominator, so cancel for everywhere. So v square equals to omega square a square minus omega square x square. Now taking omega square as a common, and we are getting a square minus x square, or in simply v equals to plus or minus omega in root a square minus x square. This is the value of velocity of a particle performing linear precession. That velocity is given by v equals to plus or minus omega in root a square minus x square. Okay, this is one of the most important formula for the linear, for the or from the chapter linear acceleration. Now we are discussing how you find out the acceleration of a particle, find out in the velocity of a particle, and the last term is the displacement of the particle, and the displacement of the particle is symbolically expressed by small s, and this is a very easy. See very carefully. V is given by plus or minus omega in root s square minus x square. Just we take the magnitude of velocity. That magnitude of velocity is v in root a square minus x square. But what is the velocity? Again it will be very clear that velocity is nothing but change in displacement per unit time. So dx by dt equals to v. Okay, dx by dt equals to omega in root a square minus x square. We have to find out the value of x. So I am writing this same equation here. Dx equals to omega in root a square minus x square multiplied by this dt. But the dx term come to this side, so my equation becomes dx into 1 upon in root a square minus x square equals to omega into dt. Again there is a differentiation on both the sides. To remove that differentiation we require the integration. So if you want to write down this part, then immediately write down. Now we require the integration part. So on integrating, now it will be very less part is remaining. See very carefully. On integrating, most of steps I am explaining. On integrating, integration of 1 upon in root a square minus x square into dx equals to integration of omega into dt. Check either it will be visible to you or not. Yes, it's visible to you. Very clearly it's visible to you. Okay, 1 upon a root. Now a is amplitude. Okay, this is a constant dx. Omega is again in root k by n, because omega square is a k by n. So omega is a constant. So my term becomes 1 upon in root a square minus x square equals to omega into integration of dx. Okay, this dx is remaining. But what is the integration of 1 upon in root a square minus x square? It will be very simple. It is the sine inverse of x upon a. Sine inverse of x upon a equals to omega t plus alpha. Here alpha is my constant of integration. Okay, just in previous case, c is a constant of integration. In the same way, alpha is my constant of integration. So it becomes the sine inverse of x by a equals to omega t plus alpha. So x upon a equals to, it is the sine of omega t plus alpha, or simply x equals to a into sine of omega t plus alpha. So my displacement equation becomes x equals to a into sine of omega t plus alpha. What is that x? X is my displacement. A is not my acceleration. A is my amplitude. That is a maximum displacement of a particle measured from mean position. And sine of omega t plus alpha. This is a famous equation of a SHM. Basic general equation of SHM. X equals to what? Displacement is given by, sir, x equals to a sin omega t plus alpha. Now we see what are the different cases of the displacement, different cases of the velocity, different cases of acceleration when a particle is at mean position, particle is at extreme position, particle is at negative extreme position. Okay, and then we proceed the remaining part. Okay, just take a screenshot or pause this video and see all the part. Now you stop here.